today. We're diving deep into the high-stakes world of cutting metal. Sounds simple, right? Well, when you're talking about shaping the super strong materials that go into things like jet engines and medical implants, it's actually one of the toughest challenges in modern engineering. So we're going to break down how we can make these materials machinable and how to do it efficiently, precisely, and, sustainably. So here's our game plan. First, we'll define the core problem. What exactly makes these materials so tough to work with? Then we'll look at the two main levers we can pull: managing all that heat through cooling and lubrication, and then designing smarter tools. After that, we'll explore the real cutting edge, where these ideas combine, and finally, we'll wrap it all up with a direct comparison of every single technique. All right, let's kick things off with Section 1, the Machinability Challenge. Because before we can get into any of the really cool solutions, we need to have a solid grasp on the fundamental problem we're trying to solve here. This really is the million-dollar question, isn't it? The materials used in aerospace or in high-performance engines are designed to be incredibly strong and heat-resistant, which is awesome for their final application, but it makes them an absolute nightmare to machine. They don't just sit there, they fight back, generating just immense heat and pressure that can literally destroy a cutting tool in seconds. And that brings us to this core concept of machinability. It's not just about if you can cut a material, but how easily and how well you can do it. The best way to think of it is like a scorecard with three main criteria. First, tool wear. How long does your cutting tool actually survive? Second, surface quality. How smooth and perfect is the final part? And third, energy consumption. How much power did you have to pump in to get the job done? These three metrics, they're the key to everything we're about to talk about. You see, the number one enemy in all of this, it's heat. So figuring out how to manage the insane temperatures and the intense friction right at the cutting point is really the first and most fundamental strategy for improving machinability. For a long time, you basically had two choices. You could cut dry, which is clean and simple, but you generate so much heat that your tools wear out incredibly fast. Or you could go with flood cooling, basically drenching the entire operation in liquid coolant. Now this works, but it's messy, it's expensive, and it creates a whole lot of chemical waste. So yeah, neither one is exactly a perfect solution. And this is what led engineers to a much, much smarter approach called minimum quantity lubrication, or MQL. Like the name suggests, instead of flooding the area, MQL uses a high-pressure mist of oil and air. It's like a super precise aerosol aimed directly at the cutting edge. This gives you targeted cooling and lubrication right where it counts, but with up to 99% less fluid than flood cooling. It's a real game changer. And wow, this chart really shows you just how effective it is. If you look at the data from a study on milling titanium, you can see the results of dry cutting over there on the left. Now, watch what happens when you switch to MQL. Boom, both the cutting force and the temperature just plummet. Lower force and less heat translate directly to longer tool life and a better quality part. It's a huge step forward in both performance and sustainability. But what if we need to get even colder? Well, that's the whole idea behind cryogenic cooling. This technique uses liquid nitrogen at a ridiculously cold minus 196 degrees Celsius to supercool the cutting zone. And the best part? The liquid nitrogen just evaporates into harmless nitrogen gas, which, already makes up 78% of the air we breathe. So it's not just effective, it's incredibly clean. But here's the cool part. Literally, the benefits go way beyond just chilling things down. The extreme cold actually hardens the tool, which makes it more durable. It also stops harmful chemical reactions right at the cutting edge, like oxidation, which is basically a high-temperature rust that wrecks the tool. The end result, as you can see, is a much happier tool and a much better final product. All right, so we've covered controlling the environment around the cut. Now let's zoom in on the tool itself and see how some really clever engineering at the microscopic level can make a massive difference. This is a fascinating strategy. You can actually engineer the tool's surface by etching these microscopic patterns, like little dimples or grooves, right onto the cutting face. And this gives us three key benefits. First, as you see in step 1, it reduces the surface area that's in contact, which means less friction. For step 2, these tiny pockets act like little reservoirs, holding lubricant exactly where you need it most. And finally, step 3, they actually help guide the metal chips away from the cut more efficiently. It's brilliant. And the results really do speak for themselves. A 2023 study found that when you combine this microtexturing with a tool coating, you can slash cutting forces by up to, wait for it, 25%. I mean, that's a huge gain in efficiency, all thanks to some carefully designed tiny grooves. Which brings us to coatings. Think of these like a microscopic suit of armor for the tool. Using a process called physical vapor deposition, engineers can bond an ultra-thin, ultra-hard ceramic layer, like titanium aluminum nitride, directly to the tool's surface. This shield is what protects the tool from all that intense heat and the physical abrasion of the cut. Okay, now we're getting to the really innovative stuff. The next frontier isn't about picking just one of these strategies, it's about combining them. And when you start merging these techniques, you can get this incredible synergistic effect, where the combined result is way, way better than the sum of its parts. So let's take a look at a hybrid approach called cryo-MQL, or CMQL for short. It's a beautiful idea, really. You get the immense cooling power from the liquid nitrogen, and at the exact same time, you're getting that pinpoint lubrication from the MQL mist. This combination just flat out outperforms either method used alone. It's the best of both worlds, superior cooling and superior lubrication. But wait, we can push this even further. Scientists are now adding nanoparticles, like tiny flakes of graphene, into the MQL fluid. These things are so unbelievably small, they can get into every single microscopic imperfection on the surfaces. And the impact of these little particles is just profound. As the research shows, they act like microscopic ball bearings, creating this rolling effect between the tool and the metal chip that dramatically reduces friction. They also help the fluid pull heat away more effectively. So what do you get? Lower cutting forces, less tool wear, and a much, much smoother surface. Finally, let's look at something completely different. Imagine a microscopic jackhammer. That's basically what ultrasonic elliptical vibration cutting is. The tool vibrates tens of thousands of times per second in this tiny little elliptical pattern. This means the tool is only intermittently in contact with the material. It's basically tapping it instead of constantly pushing. And as researchers found, this dramatically reduces the average cutting force and temperature. So we have covered a ton of ground here, from traditional flood cooling all the way to advanced nanofluids. Now, let's put it all together and do a side-by-side comparison to see how these strategies really stack up against each other. All right, this table basically gives you the lecture notes for everything we've talked about. If you look at the rows, you can see the whole progression. The old ways, dry and flood cutting, they have some major drawbacks, right? Poor performance or terrible sustainability. Then you get to the modern techniques. MQL is a fantastic all-rounder, a great balance. Cryogenic is a beast for performance. And right there at the bottom, you have the hybrid techniques. They offer absolutely superior performance while still being very sustainable. They're pretty much the current state of the art. And all of this brings us to one final, really important question for the future. As our materials get stronger, lighter, and more durable, how will our methods for shaping them manage to keep pace? This ongoing race between material science and manufacturing science is what will define the future of everything from aerospace to medicine. The innovations we've explored today, they're just the beginning of that race. Thanks for digging into this with us.